So I'd like to thank the organisers. I'd also like to say a little bit about my background in that I'm originally trained as a theoretical physicist in strongly correlated systems and superconductors and things like that. And basically since Lawrence Lowe and Paul Byrne have been here, I've got more and more interested in these systems and begun to do some work on them, but I've got maybe a lot of different training from, say, Johannes, last talk. And so I'd like to talk a little bit about my perspective on these materials. It kind of ties in quite nicely with the last talk, because I'm going to start with the same quote. Is this the laser pointer? Right. And actually, I want to emphasize the second half of this quote, which wasn't stated in the previous talk. Is that, yes, the fundamental laws are necessary for the mathematical treatment of the large part of physics and the whole of chemistry are completely known, but the difficulty lies only in the fact that the application of these laws leads to equations that are too complex to be solved. And that's kind of the problem we're faced with in both theoretical physics and theoretical chemistry. And so this kind of high throughput approach is certainly one very promising way of looking at things. But I really want to talk about kind of low throughput approaches. So what should we do about this problem? Well, one idea is to build a better computer, and certainly, computers didn't exist in 1929, and we've had this Moore's law exponential growth for the last 50 years. The problem is that the problem we're trying to solve is also exponentially difficult, and we're really not making any real progress in doing the exact solution. So the full CI calculation is only really possible still in very small volumes. So we either need, for example, a paradigm shift in computing technology. In one paper I was involved with recently, actually also some of the co-authors on this from the Asparabitsa group, we used a prototype quantum computer to study the smallest possible molecule, the hydrogen molecule, and we were able to solve that in the smallest possible basis set. So this is essentially the easiest calculation in the entirety of quantum chemistry. And this is kind of the state of the art of the field at the moment. So we did that in the quantum computer. Now there's several problems with this, I should point out. There are some steps that weren't scalable in the way we did it. So those need to be overcome to get this to be general. We're able to show that we need about 100 or so logical qubits to outperform a classical computer for quantum chemistry. However, the best experimental groups in the world only have 10 physical qubits. And the distinction between a logical qubit and a physical qubit is you also need to do lots of error correction. You need qubits to do that. And so that puts an extra, you don't really just need 100 qubits to do this. That's 100 qubits that are doing actual calculations, not counting the ones doing the error correction. And so we're probably at least a decade away from being anywhere near this, and that decade might be an optimistic number. But certainly this was a lot of fun for me. So the other approach, and really what I'd like to do in the intervening at least decade, is to think about building better approximations. So what are the key ingredients you need to understand the important physics and the important chemistry? And in particular, what are the simplest models that let me as a theorist think about those? So if you go to an introductory theoretical chemistry lecture, you'll often see a slide like this, which is kind of summarizing the problem for a chemist. So we have this exact solution that Dirac was talking about. And you can improve the quality of the approximation you use to solve this problem. Or you can improve the quality of the basis set, and don't worry if you don't understand this alphabet soup around here. It's just going this way gets better, going this way gets better, the right answer is here, easy is over here. And somehow you're limited to this bottom corner. And so, but what I really want to talk about is actually there's another axis that we often ignore, which is the quality of the Hamiltonian. And there's various different Hamiltonians I could use. Maybe when we get up here, actually, probably has to be the Lagrangians, but let's not worry about that. And this isn't just a choice axis. What it's really describing is the energy scale of the problem. So if I go off to the Planck scale, I need to worry about quantum gravity. That's really not going to affect organic photophysics in any way. If I come down, I get to the standard model, QED, the Dirac equation, Schrödinger equation. I can also go down further in energy and get to effective Hamiltonians. And this has been an approach that's been very successful in strongly correlated materials. So things like, for example, the Anderson model describes the Kondo effect that you see when you put dilute magnetic impurities into metals. It describes transport through a quantum dot, and it can describe single molecule transistors as well. So there's one very simple effect of Hamiltonian can describe a lot of physics, and it lets you understand where you see very similar things in all of those very diverse physical and chemical systems. And these are roughly the energy scales you might want to be thinking about. And of course, condensed matter physics and chemistry sit down here at the bottom of the energy scale. So some kind of use of these different Hamiltonians is really going to be what's relevant to us. And again, you can think about what method you use. And if you're not really familiar with effective Hamiltonians, often if you're from a chemistry background, you might think about semi-empirical models. And these are really just what I would call effective Hamiltonians by another name. They're things ending in DO, so Sindo, Indo, Zindo, etc. And normally they're just solved at the Hartree-Fock approximation, because they were designed when computers were much less powerful than they are today. But there's absolutely no reason you can't apply really powerful methods to these kind of Hamiltonians once they're suitably parameterized. And that's the first thing I want to talk about today. So these kind of molecules are probably more familiar to most people in this room than they are to me. And these are some very famous molecules. And one thing that it seems to me as an outsider in this field is that in both, for example, OLEDs and dioxide solar cells, there have been a few very famous molecules that have come out, and there's been a great difficulty in really improving on those. And so that seems like an interesting challenge for a theorist to think about why are these molecules so good, and how can we come up with really rational design principles to understand them. And I'm certainly not going to claim that I've done that, and I'm going to tell you what those principles are today, but I think that's a really interesting problem for theorists to work on. Okay, this is another quote I like from Michael Berry, that only wouldn't study the general case, and real scientists work by examples. So here's an example system that I want to think about. These iridium triazole compounds that were originally synthesized by Lawrence Lowe, who's in the audience somewhere. And what's kind of interesting a thing about this to me is he takes the parent molecule, there's two groups here, X and Y, and it starts off with these being hydrogen, and then he substitutes either at the X position or the Y position with a fluorine molecule. And so if he puts a fluorine in the Y position, the photoluminescent quantum yield goes down by about a factor of 2, and if he puts a fluorine in the X position, it goes down by an order of magnitude. Now, to me, as a naive physicist, fluorine and hydrogen on the scale of organic chemistry, perhaps, aren't that dramatic. Now you can argue about how dramatic those changes are, but these are really spectacular drops in there. So it seems to me, this is something that we should try and understand, why these small changes are making such huge differences. And there have been hundreds of papers making new OLEDs, and again, there doesn't really seem to be an adequate way at the moment to predict whether an OLED will be highly emissive or not. Okay, so the first thing I'm going to talk about is the effective Hamiltonian approach. And actually, this paper here was just accepted about 6 hours ago. So not quite as recent as one of the other speakers. And there's a second one that's on the archive, which is a physics preprint server. And most of this work's been done by my student Anthony Jacko. It's also done with my collaborator, Ross McKenzie. And because everyone's talked about homos and limos a bit, so I thought I'd take my turn sticking the knife in. So let's think about, and I really like Gary Rumble's names of calling this a band diagram and then contrasting that with state diagram, so I'm going to steal that nomenclature. And let's take this model seriously. Let's say we just have some organic molecule that's got a homo and a LUMO, and they're separated by an energy delta. So let's go make some predictions, because that's what theories are good for. So the ground state I'm just going to define to have energy 0. Then I can think about the first excited singlet state, and that's going to have energy delta. And I can think about the first excited triplet state, and that also has energy delta. So this is a good theory that makes testable predictions. That's the thing you should ask of your theory. Thing you should ask of a theory. If it doesn't do that, it's not a good theory. So we can then take some experimental data, and I'm taking these for various ligands that turn up in these transition metal compounds that I'm interested in, and you can see that the theory fails absolutely spectacularly. So there's roughly, factor of 2 or something difference in these energies. So this is why I don't like this talking about homos and LUMOs. And also, it also would predict, for example, that kind of picture would predict that there was no exciton binding energy. So that model clearly isn't good enough. And of course, the missing ingredient is the exchange J, which comes from the fact that these electrons are fermions and they have a Coulomb interaction. So now I can put an extra parameter in my model J, which is this exchange interaction. It lowers the energy of the triplet, raises the energy of the singlet, And of course, well, now I have two parameters and I'm fitting to two data points, so I can get the perfect agreement with this theory and this data. But that's not the point that I really want to emphasize. But you go ahead and calculate it, and you get delta, and you get J. And one thing I want you to notice that's going to matter in a moment is that delta is, 3.5, give or take, maybe half a volt. Whereas J is well, say 1.5 plus or minus 1. So J is varied by a lot, and delta isn't varying all that much. Okay, so now let's think about a fragment model for an organometallic complex. So we're going to have our HOMO and our LUMO from the ligand. And for simplicity, I'm just going to think about one ligand, I'm just going to think about one metal orbital. So I still have my delta, which is my splitting, I still have J. I also have the splitting between the HOMO and the metal, which is epsilon. And then I'm going to allow electrons to hop from the HOMO onto the metal, like this is parameter T, or hop from the metal onto the LUMO, this is parameter TL. And also I want to include all the possible direct Coulomb interactions. So there's a U between two, that's the Coulomb interaction between two electrons both on the HOMO, same thing on the LUMO, same thing on the metal, and we have V's, which are the Coulomb interactions between the two electrons in any of the given orbitals. And this model the nice thing about this model is it's sufficiently simple that we can do the full CI on it. And in fact, we can make really quite a lot of progress even analytically in this problem. And when we do that, it turns out that there basically turns out to be one key parameter, which is this epsilon star minus J on 4. But before I can tell you about that, I need to tell you what epsilon star is. So actually, most of those parameters in the previous model, we can estimate either from looking at the properties of the constituents, so just looking at a ligand. I showed you how to get delta and J already. Or by doing some semi-empirical calculation. And the one that turns out to be quite difficult parameter to get is epsilon, because this is really a property of the complex, not of one of the isolated fragments. And when I put on interactions, then I get this epsilon star, which depends not only on the original energy gap, but also on the difference of these direct Coulomb interactions. And one thing to note is this epsilon star, turns out typically it's probably pretty small, so maybe less than a volt, whereas these things are all several volts, and so small changes in these, percentage-wise, can lead to quite large changes in this, percentage-wise. And so we already saw that we expect large changes, variation in J across different complexes. Now we can also expect large changes in epsilon star. So this thing we expect to change quite rapidly as I tune the chemistry. And it turns out that the photophysical properties are going to be very sensitive to this value epsilon star minus 4J. And that's basically because it's the energy splitting between the two lowest lying triplets, which is MLCT ligand charge transfer slot, where I take an electron from the metal and put it on the LUMO, and this ligand-centered excitation, where I take an electron from the HOMO and put it on the LUMO. And so, if we go ahead and solve this model, so this colour scheme, when it's green, this basically means that it's this pure green, it's a pure MLCT triplet. If it's pure red, it's a pure ligand-centered triplet, and as the colours merge, it's telling you what the mixture is. And this blue dashed line is the lowest lying single excitation. And there's basically two regimes. So if I have a small epsilon star minus 4J, then we have predominantly ligand-centered solution, lowest lying triplet. And as I make this parameter bigger, then we get a metal to ligand charge transfer triplet being the lowest energy. And for a number of OLED materials, it's been argued by various both theoretical and experimental methods that the T1 state is basically MLCT, and this would put us out in this region over here. I think there's a sign error, that's sign there. And particularly in this region, the S1 to T1 gap is strongly dependent on the ratio, on the value of this parameter here. So one thing you can think about, which is perhaps isn't so important in these systems, but certainly important to other kind of molecules we're thinking about, is what happens when I inject two charges in? Will they form a singlet and a triplet? And I guess in the first session this morning we had a lot of discussion of that kind of thing. And one thing to see, at least in this model, that you don't just get this 75%, 25% that you get by counting spins. But because as the interactions vary, this can go from being pure triplet down to down towards this 75-25% ratio. And so this really, once you put interactions into your model, that 75 number is not at all robust, as the key points take away from this slide. And so I can also look at the radius of decay rate if I include a spin-orbit coupling in the model. And you can see that this is a log linear plot. And so this triplet radius of decay rate goes virtually, it's almost a straight line on this log linear plot, which would suggest an exponential. Actually, I think it's probably just a big power law, so something like the fourth power of this small parameter. But then it's where you see, when you make, I've argued that chemistry is going to change this parameter quite strongly. And so that's going to cause massive changes in the radius of decay rate. And you also expect the non-radius of decay rate to depend sensitively on these parameters because it's an exponentially activating process. And so this model, at least qualitatively, gives us the prediction that as you change the chemistry, you can see just little changes in the chemistry can cause very large changes in the PLQY, and that's what you see experimentally. So now I want to move on to talk about something slightly different. This work has been done by a range of people, some of whom are in the room. Particularly I want to point to Arthur Smith, who's a PhD student who's done all the calculations and most of the experiments that we're about to talk about. So again, I'm going to stick to my favourite example molecule, these triazole compounds. And here's the photoluminescence and the absorption. And you see they look very different, and they don't look much like a mirror image. So there's a subtle error on this plot, which many people, spectroscopists in the room, are aware of, and I'll point it out later in the talk. But it looks very different than the normal mirror image plot. And so, does that suggest that there's really significant geometry relaxation in the excited state? So certainly people have suggested that in various compounds that look like this, or just that the absorbing state is not the emitting state. And I'll come back and talk about that. So Arthur also did a lot of MCD, or magnetic circular dichroism experiments. And what you do there is basically you put a field on your sample, and then you look at the absorption with right-hand polarized light and left-hand polarized light, and you take the difference of those two things. And that can tell you something about the energy levels you're seeing. So there's three kinds of things you can see. There's a Faraday A term, which arises when you go from a non-degenerate ground state to a degenerate excited state. And it gives you this kind of characteristic differential form in the MCD spectrum. There's a Faraday B term, which is when you get a mixing of energy levels caused by the field, and that just looks like a regular kind of peak like you would see in any absorption spectrum. There's also a C term, but we're not going to see those, so I'm not going to talk about that. And so here's the data. This is all done. All this data is taken at 10 kelvins at both the absorption and the MCD up there. And what I've done is compared this to a kind of standard TDDF, time-dependent density function theory calculation. And this is the kind of standard workhorse of what most theorists do to look at these kind of complexes. And, you know, to some level, we're getting a reasonable agreement. We've got a big peak over here, there's a big peak in the spectrum, there's a big peak here, there's a big peak over there. I should stress that we're going to look at a lot of these plots, and we're doing DFT-type calculations. Any differences that are, say, a tenth of a volt are just, you know, DFT is never going to get that right within the last tenth of a volt, so we're not going to worry ever about differences between peaks and a tenth of a volt in the experimental theory. That's just a limitation. The problem thing I am worried about here, so these things are very small, they're the triplets, and I've just given them an arbitrary weight because they're formally forbidden. But what you see is there's all this structure down here that we can't really explain, and the MCD is going crazy in this region, so all kinds of spikes, and we've really got no states to describe that. So something's wrong in this calculation. It's not doing a good enough job of explaining the data. So there's various things we can do. One is to crank up our method. We could do something much better approximation, the kind of thing that Johannes just talked about. And then it's this nice thing by Powell. They look at complete active space kind of methods. And it's kind of difficult to do. That's a real tour de force calculation. These are big molecules. That's a really tough thing. But also another thing we know matters is relativity in these. So we can see that experimentally. So there's phosphorescence, there's fast intersystem crossing, and both of those effects are basically forbidden unless there's a spin-orbit coupling. And so spin-orbit coupling has a relativistic origin, and so we know that relativity is playing at least some role in this system. And another important thing is if you construct a perturbation theory, the Dirac equation around the low velocity limit, spin-orbit coupling appears at second order, whereas the largest corrections appear at first order. And so we know that this isn't the biggest relativistic correction. So there are some well-known relativistic effects in chemistry. Perhaps the nicest one, like this gold medal of Einstein, the connection to relativity, is the colour of gold. So why is gold a different colour than silver? They're right on top of each other in the periodic table, they should look the same. So there's an important transition involved. For silver, there's a 4D to 5S transition, and that's in the ultraviolet. So it doesn't affect the colour, you can see. In gold, there's a relativistic correction for the 6s orbitals, actually for 5D as well, which lowers the 6s, pulls them closer into the nucleus, and therefore lowers their energy, because they're moving closer to something that's got an opposite charge. Actually does the opposite to the 5D, so that enhances this effect. And so that lowers that energy and brings it into the visible, and that's essentially what gives gold its gold colour. Of course, the detailed explanation is quite complicated by the fact there's surface plasmons, and working out the actual colour of the material is tricky. But basically, this is the core of the effect. And certainly, if you do calculations without relativity, you find that gold should look like silver, basically. And if you put in relativity, you find it consistent with the experiment. That's kind of easy to understand if you know a little relativity and a little quantum mechanics. So basically, if something's moving with a high velocity close to the speed of light, its mass gets enhanced by this amount here. So m0 is the rest mass, m is the actual mass. And if you put that into the calculated Bohr radius, you find that gets smaller. So the radius gets smaller, the energy gets lowered, you're putting a negative charge, likes to be close to a positive charge. Okay, this has a lot of maths on it, which I think either people will find obvious or intimidating. So I don't want to spend too long talking about it. The key point is that when I solve the Schrödinger equation, I have a wave function, and that's hard enough already. When I solve the Dirac equation, I have a spinner, and so that's like having 4 wave functions, basically. And this tends to make the calculation about 2 orders of magnitude more expensive. So this is not fun for theorists. Okay, so I'm going to start cheating to get rid of some of the difficulties that I don't, cheating, making approximations, I guess. Difficulties that I don't want to deal with. So one complication in relativity is that interactions are retarded. Nothing can go faster than the speed of light. That obviously includes light, and light carries the electromagnetic force. And so really, if I do a full relativistic calculation, I should worry about that. I should worry about the finite time it takes for the photon to get from the electron to the nucleus or something. That's too much hard work. It would take you down you have to end up doing full QED calculation, and that might be incredibly expensive. We're not going to do that. So we're going to work in the Born-Oppenheimer frame, which is just a frame where the nuclei are stationary in. And that means the Coulomb potential gets changed and looks like this, where U1 and U2 are the velocities of 2 electrons. So it does make our theory much more tractable, but it does mean it's not Lorentz invariant anymore, which is the price we have to pay. The other thing I'm going to use a lot is a spin-free approximation. So there's this problem that the force spinner is causing us all these problems, and so I can rewrite the Dirac equation like this, where there's a term that's spin-free and a term that's spin-dependent. And so this spin-dependent term, for example, would include the spin-orbit coupling. But this can be written in a way that looks almost exactly like the Schrödinger equation. And so I can use all my methods I'm used to for the Schrödinger equation. And this has the lowest order corrections, so like they're going like I can say they're going like 1 on C squared, which is the normal expansion that people who study some QED, but actually for chemistry it turns out better to expand on this factor and this factor. But this has a lowest order correction and this has a second order correction. And so this is the dominant term, and what we're going to do is make the approximation that I can just solve this Hamiltonian, and then just include the spin-dependent terms perturbatively at the end. Okay, this slide's really for the experts. I'm just going to leave it here for a second and let them read it. Some details of the calculation. Basically, we were doing TD-DFT, important thing. And I want to say something now to the non-experts about the difference between DFT and TD-DFT. This comes back to this difference again between this band picture and this state picture. And what I'm saying here is a little too strong, perhaps, but the spirit, I think, is right, and probably the experts are aware of the caveats, and I won't go into talk now. So the simplest way, if you interpret DFT in its simplest way, which is actually what most people do most of the time, DFT really naturally gives you HOMOs and LUMOs, and it gives you this band picture. So TDFT is basically something that sits on top of that and turns that band picture into a state picture. And that's the way it's kind of a nice way to think about it. And it also allows you, doing that allows you to then map back and forth easily between the band picture and the state picture, and that can be useful for getting insight. And there are many caveats to that statement. and I'm sure all the experts know them, but that's not really for you. Okay, so now we can go and do our scalar relativistic calculation. So sorry, our page not split into calling it scalar, that just means the spin-free calculation. And we can see this has a dramatic effect on the spectrum that we calculate. So now we've got a nice big peak here still, a nice big peak here, and we've got several states getting moved down here where all this MCD stuff is, and where these things are. So this already seems like quite a big improvement over the non-relativistic calculation. Of course, I've still got triplets that have a forbidden transition, so all these things I've just given them an arbitrarily small weight, so you can see them, but they're still not really there. And so let's go ahead and put in the spin orbit perturbation. And so now it doesn't change the details down here too much, but there's quite a big change down here, and we're getting a lot of states down here where the MCD is seeing stuff and where the absorption spectra are. Okay, so all those calculations so far were just for the parent compound where it was fully protonated. Now here are the different compounds where I put the fluorine in, and you see again, always we get these kind of two big states and a bunch of states down here, and they seem to agree quite nicely. I want to show you these two plots are basically the same, the colour coding is just different. So this is telling you how much MLCT there are, so this is all kind of MLCT, at about 50% of this is MLCT roughly. Most in these, and this is telling you how strongly these things are singlets, how strongly they're triplets. So the green is really pure singlets, and the light blue is really pure triplets. And then there's some mixture down here. Okay, and I can also do Ripley, which is this very famous compound. And again, we see the same kind of thing. So non-relativistic, the peaks are a bit too far. High energy, down here they're a bit too red, but pretty good. And again, there's the only real states at low energy, and we see a few coming in when we do the relativity. But interesting, we don't see very much in the MCD down here, which suggests that these states are weak, and so we're at least qualitatively getting that right. Okay, so now we'd like to understand, I mean, if I go back to these, let's go back a couple of things. One thing that's not immediately obvious, it wasn't immediately obvious to us, is why there's such a big change between the non-relativistic and the scalar relativistic. So it's kind of intuitive that singlets and triplets are going to get mixed when I put spin orbit coupling in. That kind of makes some natural sense. But why is there such a big change here? Okay, so these are the homos and the lumos. I can now use this to make, I've said that quantitatively this is not going to give me the right answer, but qualitatively it can give me some insight. So we're allowed to talk about homos and lumos as long as we just make qualitative statements, I think. And so what we find, these are C3 symmetric molecules. So the homo is non-degenerate, it's an A level, and the homo -1 is twofold degenerate, it's E, and the same is true going up in energy, so the lumo is A, and the lumo +1 is E. So these are the DFT orbitals we get from a non-relativistic calculation. If I do a relativistic calculation, basically nothing changes. So it looks exactly the same structure. If I can flip quickly between those, you can see there are some subtle differences, but I don't want to claim anything important has happened by those differences. But what I do want you to notice is that each of the homos has a strong contribution from the iridium d orbital, whereas in the lumo there's basically very little weight from the iridium. Okay, and this is the basis of our understanding of what's going on. If we look at the energies of these homo and lumo levels, I've written in the actual numbers for the parent complex, but the story is basically the same for all four. So the lumos are sat here like this, the homos are sat here like this. When I do the spin-free relativistic calculation, the lumo doesn't really move at all. But that's not that surprising. There's very little weight of the lumo on the iridium. All the relativistic effects are coming from the iridium, and so we don't see any change. But the homo sees a big shift up in energy. And we just kind of understood this yesterday, basically. So what Arthur did, it was a very smart idea, what Arthur was going to do, is to go off and do the calculation for the isolated iridium atom, just by itself. And what you see there is that the D levels, and when you go from non-relativistic to relativistic, the D energy level is getting pushed up by about this kind of amount there. So we think that's where it's coming from. We think that's probably a known effect that's understood by atomic physicists, but at the moment it's not understood by us, and so we have to work that out. But this is, in terms of the calculation, this is clearly where the changes in that energy level structure is coming from, and these kind of size changes tie up very nicely with what you're seeing in the actual CPGFT calculations. Okay, so let's go back and try and understand what these transitions are in terms of, so we've got our state diagram here, we've got our band diagram here, and we want to try and join the two things up together, and I'm nearly at the end. And so first we want to look at this dominant singlet here, which are the S4, S5 singlets, and they correspond to these 95% of the weight of these transitions is coming from the HOMO minus one up to the LUMO. Again, 96% for this big one here is coming from the going from the HOMO to the LUMO plus one. And so but these levels are getting shifted around by the relativistic correction, so we can see that the big shifts in here are kind of naturally explained by the moving of the HOMOs and the LUMOs. And I also want to understand this triplet down here, which could be important. And that's a slightly more complicated system answer, because not only is the energy levels moving around, but also the weight. This is, in the non-relativistic calculation, there's only about half a HOMO-LUMO transition, whereas in the relativistic calculation, this is much more just like a simple HOMO-LUMO, though it still only has 72% character of that. We can explain the MCD at least qualitatively and probably quantitatively. I won't say that, oops, but I do want to show the last thing is that if we plot the absorption on the same plot, then this triplet seems to lie very nicely underneath the first maximum in the emission, sorry. So now I can tell you the something I did wrong here, of course, I should know about Cash's rule. Emission always happens from the lowest energy state, so I shouldn't normalize to this maximum, I should normalize to this maximum here. If I put the 10 Kelvin data on top, you see which really is a maximum. If I scale them up, it'll be the same height. Then you can see this looks very nicely like there's a mirror image here. It's probably going to come down again, but there's this other peak overlapping with it. We don't yet have 10 Kelvin emission. We're going to do that, and that will be a good test of that. So this suggests that there is a mirror image rule, that that is phosphorescence, which isn't that surprising, and that there's no significant geometry relaxation. In conclusions, so I think really a key thing to take away, I think, is that different theoretical approaches can give you different insights, and maybe even different types of insights. So we saw that small changes in the chemistry cause really large changes in the photophysics, and then we can explain that quite naturally from this effective Hamiltonian approach. Relativistic effects clearly make really important changes in these molecules. I looked at there are OLEDs, but many of those conclusions I think will also be applicable to dose-sensitized solar cells. Although of course we need to go and do that, I'm sure that's true. And an important idea is that for the accurate description of the spectrum, you need to include both the scalar relativistic and the spin orbit. So people have looked at the spin orbit before, but as far as I know, we're the first people in these systems to really include that scalar correction. That seems to be absolutely vital. And it looks like it's good enough to really make quantitative predictions of what these OLEDs will look like. So, and that's something we're trying to do at the moment with some other molecules that have been made in the group that I'm not allowed to tell you about. And an interesting question I think this poses. So we've talked a lot about electronic correlations, geometry realization, salvation effects in these molecules. The fact that, at least in this one system, this relativistic TDFT seems to do so well, would at face value suggest that these things aren't really playing an important role. That is certainly counter to my intuition about the problem. Happy to be wrong there. But the other thing it could suggest is that we're getting the right answer for the wrong reason, and I think really we need to think much more carefully about that. So thank you for your attention.
Your calculations where the Zora inclusion gave this nice shift upwards. Did you try what happens when you change the amount of exact exchange?
No.
That might be interesting.
Yes.
Because that local level, the local always should have an effect on the relativistic.
That's a good point. Yeah.
I've got one more which is slightly off the topic. Your explanation for the goal. The question why is colloidal, so the reason for colloidal gold being red is there not relativistic effect, right?
No, that's due to the changes in the surface plasmons, which Chris Parnell spoke about. You spoke about earlier, right? So maybe you but that's nothing to do with that transition. It's a plasmon effect. It's the short answer. But I know nothing more about plasmons than what I learned in
Let me ask probably a naive question. We've heard a lot about singlet triplet intersystem processing. absolute values for those rate process? And how sophisticated are the basis that they use for that?
So that's one thing that's on our to-do list, is to, certainly, I mean, the thing that's kind of easier for us to calculate would be the relative lifetime of the triplet state. And in principle, we get that from the calculation, but it's kind of hot off the press, so I don't know. In general, I'm not aware of a good way of getting that intersystem crossing rate, certainly from this kind of first principles type calculation.
That's a tough one.
That's a tough one, I think. But maybe, I don't know anyone else.
Factor 10. You can do it to a factor of 10. Well, the actual rate's 10 microseconds, and you might calculate 9 microseconds.
That's quite sufficient. If there are no further questions, we can make our speaker one more time. So next up, very important group.